So, have you ever really thought about what it takes to stream a live IPL cricket match to millions of people all at the exact same time? This isn't just a matter of hitting a broadcast button. It is one of the most intense engineering challenges on the planet. And, understanding how it's done can give you a massive edge, especially in interviews. So, let's dive in. We are talking about 20 million concurrent viewers. Now, to put that number into perspective, that's like the entire population of Mumbai and Delhi combined, all hitting play at the very same moment. And every single one of them is expecting a flawless, buffer-free experience. No pressure, right? It's a fantastic question, and it's also a classic system design problem you might run into in a tech interview. How do you actually build a system that can handle that kind of mind-boggling, unpredictable demand? Well, the answer starts with a huge shift in how we get video in the first place. Yeah, if you were using the internet back in the early days, you definitely remember the pain of trying to watch a video. The technology has come such a long way, evolving from a simple download to a much more sophisticated, intelligent stream. So, the old way was called progressive download. The server would just send you the entire video file, and you'd have to sit there, staring at a loading bar, waiting for enough of it to download before you could even think about pressing play. It was painfully slow and a huge waste of bandwidth if you decided you didn't even like the video. But the new way, adaptive streaming, is so much smarter. The video is delivered in these small, manageable chunks, and you start playing it almost instantly as it arrives. Okay, so adaptive streaming is the secret sauce. But what does that adaptive part really mean? Let's break down the core tech that makes all this modern streaming possible. It's basically a three-step process to get the video ready. First, you encode. The original, super high-quality video is converted into a bunch of different quality levels, everything from glorious 4K all the way down to a grainy 240p. Second, you segment. Each of those quality versions gets chopped up into small pieces, usually just a few seconds long. And third, you organize. All the info about these different pieces is put into a special file called a manifest file. And that right there brings us to the most important piece of the puzzle, the manifest file. Just think of it like a menu for your video player. The player on your phone reads this menu, it checks out your current internet speed and screen size, and then it intelligently orders the perfect chunk of video for you. If your connection suddenly gets worse, it just orders a lower quality chunk for the next segment. If your Wi-Fi kicks back in, boom, it orders a high quality one. This is what makes the whole experience feel so smooth and seamless. Now, knowing the theory is one thing, but actually applying it when 20 million people are watching, that's a whole different ballgame. So let's step inside the GeoCinema engineering war room during a massive IPL match. The engineering team has this one critical question that they ask themselves constantly. Will this survive your Dhoni spike? A Dhoni spike is exactly what it sounds like, an unpredictable, absolutely massive surge in traffic when a superstar like MS Dhoni walks out to bat. The system have to be ready for millions of new viewers to flood in, literally in a matter of seconds. So to get ready for this, the team goes into a war room hours before the match even starts. They proactively scale up all their infrastructure. We're talking servers, databases, the whole shebang. They do a full review of all the system metrics to make sure everything's in the green. And they get all their partners, cloud providers and content delivery networks, which are servers all over the world that help deliver content faster. They get every single one of them on a single conference call. A core principle here is just aggressive caching. The main goal is to have those content delivery networks, the CDNs, handle almost all of the traffic. The entire system is designed to protect the main servers, what they call the origin, at all costs. If more than 10% of requests manage to get past the CDN's cache and actually hit those origin servers, that's a huge red flag. The real engineering challenge is keeping that number as low as humanly possible. But even with all this incredible planning, things can and do go wrong. During one IPL season, the engineers saw this sudden, terrifying spike of 10 million requests per second hitting their image servers. It was threatening to take down the entire app. It wasn't the video stream, it wasn't the homepage. So what on earth was it?
Stickers. That's it. A fun, seemingly harmless little feature.
So here's what was happening. When a user clicked to see the stickers, the app was downloading all 50 of them as separate individual image files. So one click from one person created 50 requests. Now multiply that by millions of users, and you get a system-crushing traffic storm. The solution was actually simple, but totally brilliant. They just bundled all the images into a single file. This one change dropped the traffic from 10 million requests per second all the way down to just 100,000. Incredible. This whole sticker incident really highlights the core philosophy you need to operate at this kind of scale. It's not about preventing failure. It's about anticipating it and designing a system that can handle it gracefully when it inevitably happens. And here is the single most important point. At this scale, you just have to assume that failure is inevitable. It's not a question of if, but when. Whether it's a database overload, a network failure, or a sticker-induced traffic spike, something will break. The entire engineering strategy is built around this one simple assumption. This is exactly why you can't just rely on auto-scaling. As one engineer pointed out, when a database hit 100% capacity, it took them 45 minutes just to add 5 more servers, or nodes, to the system. By then, half the match was already over. You can't be reactive. You have to scale everything up before the game even starts, all based on really careful planning. So what happens when a critical system does fail? Well, they have something called panic mode. Before the match, they take a snapshot of a normal API response, which is basically the data the app needs to work, and they save it as a simple static file. If a backend service goes down in flames, they flip a switch and the CDN starts serving this safe, pre-saved version instead. It might not be personalized, but for the user, everything looks totally normal, and most importantly, they can still watch the match. And this is a brilliant example of a concept called graceful degradation. Features are categorized. You have P0 or priority 0, which is the absolute core experience, playing the video. Then maybe P1 is personalized recommendations, and P2 is interactive widgets. If a P1 or a P2 feature fails, the system is designed to just let it fail silently, without ever showing the user an error message. The core P0 experience, the stream, is protected at all costs. So after diving into all this tech and the war room stories, what's the big lesson here? Well, the core philosophy isn't about trying to avoid failure. It's about controlling it. It all really comes together like a fortress. Adaptive streaming is your foundation. Aggressive caching, that's your strong outer wall, your main shield. You build this fortress before the battle even starts with proactive scaling, because you know you can't build it fast enough once the attack begins. And at the very top, in the safest part of the castle, is the core mindset. You design for failure with smart strategies like panic mode and graceful degradation. And that leaves us with one final question, especially for those of you out there preparing for system design interviews. It's easy to design a system for the happy path, right? The one where everything works perfectly. But the real challenge, the thing that separates a good system from a truly great one, is engineering for that inevitable moment when things go wrong. So are you planning for that?